Hello and welcome to Lecture 7. This lecture is about multiplication and division operation in assembly. We have talked about these two operations in previous lectures, but in this lecture, we are going to study these two operations in more detail. Let's start with the multiplication operation. Multiplication has two forms in assembly. One is for the unsigned number, which is small, and the other one is for signed number and it's specified with I mul. So we start with mul operation. So mul operation has only one operand or argument, and in here we specify that with source. So the source could be a register like EBX, ECX, EDX, and or could be like memory location specified by a variable like num1, num2, and so on. All right, let's see more detail about mul operation. Okay, source could have different bit lengths. It could be 8-bit, could be 16-bit, 32-bit, or 64-bit. Depending on the length of the source, the command itself is going to automatically choose the second operand. So if the source is 8-bit, then the second operand would be AL, meaning that it's going to multiply AL with the source and then put the result into AX register. As you know, AX has a 16-bit length. Has 60-bit length, whereas AL has 8-bit length, and for the first command also source is 8-bit length. And why is that? Why we choose the result in such a way that the container for the result in such a way that it is somehow twice in bit length than the first two arguments. The reason is that when you multiply two numbers, you have to consider the worst case scenario in terms of the number of digits. So for example, for multiplication of two decimal number, you could have 1 multiplied by 1 and the result is 1. And then you could have, for example, like this, 8 multiplied by 7, which is 56, and then the maximum number could be 9 multiplied by 9, which is 81. So it means that in worst case scenario, when you multiply two numbers, the bit length or the length of the resultant could be twice than each of those arguments. So in here, for example, 9 by 9 is each are 1 digit, but the result is 2 digits. And 8 by 7, 8 and 7 are 1 digit, and the result is 2 digits. We can try this for also for higher digit numbers, like for example 12 multiplied by 98, and then you will see that the result is more than 2 digits, and for this case the result is going to be 4 digits. Therefore, when we do the multiplication, we have to consider the worst case scenario in terms of bit length or digit length. So for binary, the worst case is that we consider the bit length as much as the summation of each bit length for each argument. For example, here, AL is 8-bit, then source is 8-bit, then the result is going to be 16-bit. In here, source is 16-bit, AX is 16-bit. The result is going to be stored in DX concatenated with AX register, which is 32 bits space, but each of these are 16-bit space. And the last one is source is 64-bit. We know RAX is 64-bit, and the result is going to store in RDX and RAX concatenation, which is 128-bit. As you can see in here, for the mul operation, register A and register D are both involved. Let's see illustration of this mul operation. That for source 8, source 16, source 32-bit, and source 64-bit. So for all these cases, in here we have shown which register is going to be used as a second operand and where the results are going to be. We have some example in this page. So we have mul B1, where basically B1 is 8-bit, which is our source. Therefore, what we are going to have is this one. So we're going to be having AL multiplied by BL, and the result is going to be stored at register AX. We know this from the previous slide. In here, we said that when the source is 8-bit, in this case is BL, it's going to be multiplied by AL, and the result is going to be stored in register AX. Let's take a look at the second one. Now we have BX. BX is 16-bit. Therefore, what is going to multiply with BX is AX register. So AX is going to be multiplied by BX, and you know each of these are 16-bit. Therefore, the result is going to be stored in the space of 32-bit. Therefore, the result is going to be stored in concatenation of two registers DX and AX register. Therefore, we're going to be having DX concatenation in AX register, which this one is 32-bit. The rest of the example are, we can follow similar strategy. Here is EBX is 32-bit, therefore it's going to be multiplied by EAX, and the result is going to be stored in EDX, EB, EAX, as shown in the previous slide. And finally, the last one is 64-bit, therefore RBX is going to be multiplied by RAX, and the result is going to be stored in RDX concatenated with RAX. This one is 128-bit, and each of these are 64 bits only. What if the source is a memory location? In here we have L1 defined as an array of data 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 numbers that is stored in L1 as an array, and we know that L1 is a memory location, and in x86 architecture it is byte addressable. So when we say L1 multiply L1, depending on the length of L1, then the multiplication operation is going to choose one of the value for the A register. It could be AL, AX, EAX, and RAX. Since here L1 could have 8-bit, 16-bit, and 32-bit length, and also 64-bit length, then this command needs some more extra information to be understood by the compiler. Therefore, you cannot use mul L1 simply. You have to tell the compiler what is the length of the word or the data that is stored in L1 that you want to use. If you say mul byte, means that take only 8-bit from the array and then multiply it with 8-bit of A register, which is AL. Therefore, in this case, is going to take L1, 8-bit only, which is going to be this one, FF, and multiply it by AL, and put the result in AX. If it says word, then whatever we have in L1 has to be 16-bit. Therefore, when we dereference L1 here, we take 16-bit of data, and then we multiply that with the value of AX. And if it is D word or 32-bit, then we take 32 bits from the array, and we multiply that with EAX register, and I put the result in EDX and EAX. You can follow the same thing for this, but remember, when you work with memory, you need to know what the bit length in memory you are going to multiply with your A register. And for that, you need to use this keyword before you dereference the memory location L1. Okay, we talked about unsigned multiplication. Now we are going to talk about signed integer multiplication. Again, in here we have the source, and our source could be 8-bit, 16-bit, 32-bit, and 64-bit. We have the same choice of, the second operand from register register A, which could be AL, AX, AX, and RAX. Let's see if there is any other thing that is kind of different from the unsigned operation. As you can see here, we also have the same thing as mul operation. The things that are different in here, for imul operation, we have different form of the syntax imul. We have imul source, which is similar to mul multiplication. And then we have imul with two operand, destination and source, where our destination register could be the multiplication of the destination operation with source operation. If we have three operand, then we are going to have this form of multiplication. Source 1 is going to multiply by source 2, and the result is going to be stored in destination. The question is, what are the form for source, destination, source 1, and source 2? If you use this form of multiplication, your source could be only a register or memory. And if you use this one, then your destination has to be a register, but your source could be a register, memory location, or some immediate value, like some numbers, 2, 3, 10, 100. And in here, you have destination, source 1, and source 2. Source 1 has to be register or memory, where source 2 could be an immediate value or a number like 100,000 or million. But you have to make sure that when you choose source 1 only has to be register or memory. This cannot be some immediate value. And also destination has to be a register. You know that for the first one, imul source, the destination is the combination of A and D register, as explained in the previous slides. All right, so we have a practice example in here, which is the factorial. We want to see how we can use multiplication operation to compute the factorial of a number. So in this program, we want to read an integer and print its factorial to the output. We assume that the result is not going to be greater than 32 bits. Okay, so the program starts like this. So we read an integer from the keyboard. We move that value into ECX register. And then we initialize EAX with 1. And then we start doing the multiplication in this loop. Let's draw the table for it. So we have EAX register, and then we have ECX register. ECX register is contain the number that we read from the input. Assume that in here we read number 4, and then when you call read integer, it's going to get the data, put it in EAX register. So we read that, now it's in EAX register, we move EAX into ECX register. Therefore, the value of 4 is going to be in here, and then we move number 1 into EAX register, and now 1. So if, say, iteration 0 going to be this value for EAX and ECX. Let's start the loop and going to iteration number 1. So in iteration number 1, we say mul ECX. If you remember from the previous command, what happened here is you have your EDX register concatenated with your EAX register. It's going to restore your result. Multiplication is going to be your source, your EAX register multiplied by source. In this case, our source is ECX register. So this is what is happening when you call mul. So now we have register ECX as 4, and then we have register EAX as 1. Therefore, we are going to have 4 multiplied by 1, which is 4. This value is going to be stored in EAX register concatenated with EDX register. Therefore, the result is going to be in here. Stay in EAX register. How about the value of ECX in the first iteration? You know that the loop is going to decrement the value of ECX register by 1, and then compare the result of ECX with 0, and if it's not 0, it's going to repeat the loop. Now it decrement the value of ECX is going to be 3, and it's going to the loop and do this multiplication again. This time, it's going to multiply EAX, which is 4, with value of ECX, which is 3. And therefore, we're going to have 4 multiplied by 3 going to EAX register. And then ECX is going to be 2 because loop is going to decrement that. This is done to iteration 2. Let's see iteration 3. Iteration 3, again, we have mul ECX in here. ECX is 2 and EAX is 4 by 3. So therefore, we have, which is 12. We have 4 by 3 by 2. Therefore, here we have 4 by 3 by 2. And then what happened to ECX? ECX is going to be decremented, and therefore it's going to be 1. And is it 0? Not 0. Therefore, it's going to go up and repeat one more time. This time, we're going to have value of EAX multiplying by ECX, which is this time 1. And then the result is going to go to EAX. Therefore, EAX would be 4 by 3 by 2 by 1. And then ECX is going to be decremented. It's going to be 0 this time. This is iteration 4. And then in loop command, it compared ECX with 0. And since ECX is 0, it's going to go down. So it's not going to repeat the loop again. Therefore, it's going to repeat, it is going to print whatever is in EAX register. And then, which in this case is this value, which is 4 by 3 by 2, which is 24. And then it's going to print a new line, and the program is going to be terminated. Therefore, this program prints out the factorial for us. Okay, let's now consider the factorial program, and this time we add a snippet to the program that print out the error message in case the result is out of range. And for our range here, we consider only 32 bits container. So let's see what is going to happen. So when you do the multiplication in here, basically, so when we do the multiplication, as mentioned in the previous slide, we are going to have EDX register concatenated with ECX register, and then our EAX register is going to be multiplied by ECX register. We said that Okay, it's going to be EAX register. Okay, EAX concatenated with the EDX is going to be the destination, and EX multiplied by ECX is our two operand. So we said that if the result is greater than 32 bits, right? Therefore, we're gonna get print out the error message. So this one is 32 bit. As soon as we get some value in EDX register, we know that the result is greater than 32 bit. And in that case, we want to print out an error message saying that the result is greater than 32 bit. Let's see how we can do this. Okay, we are defining a message here out of range. It is for when the result is greater than 32 bit. We read the integer. We put the integer in the ECX. We initialize the AX with 1. Here is our loop command. But in this time, we do the multiplication by ECX. We put it in these two registers, but we check if the register EDX has value which is not equal to 0, then we jump into the error label. When in error label, we just move the message, the error message into EAX, and we print that out using the print string. So in here, note that as long as the value of the multiplication is less than 32-bit, EDX is always 0. As soon as it goes above 0, then this is going to be true. Therefore, we are going to be directed into the error label. Okay, so if the result is not greater than 32 bits, then we compute the factorial and then we end the loop, and then we go to this line and then print the factorial value and print new line, and then in here we jump to the end line, which is end of the program. Okay, now let's take a look at the division operation. As in multiplication case, we also have two different forms of division, div and idiv. Div is for unsigned division, and idiv is for signed division. So we have the source here. In these two cases, source could be register or a memory location. Let's start with this syntax. Division source 8. When the source is 8-bit, what's going to happen? Again, as you can see from here, register AX is always involved. So when you say div source 8, it takes the register AX, it divided with your source or your operand, and it put the result in AL register. As you can see here, the resulting container AL is half of AX and their source. Half of the AX register. AX is 16-bit, but the result is going to be less than 16-bit, and in our case, since it is divided by the 8-bit register, the result is going to be 8 bits, having 8-bit length. And then we also able to calculate the remainder in this operation. The remainder is going to be stored in AH register. So you have your AX, you take the remainder, and then you put the remainder in AH. So here is an example of it. You have div bh. It means that you take the register AX, you divide it by the value of bh, and then you put the result into AL register. And then in AH, you will take the value of the remainder. AH going to have the remainder of the division operation. And then, as we said previously, when you want to work with the memory, you have to tell what bit length of the memory you want to use. Here we said byte, means that our source is 8-bit. Therefore, again, we use AX divided by L1, and then you put the result in AL, and you put the remainder in AH. Therefore, AH is going to be the remainder of AX divided by L1. Okay, here we have an example where our source is 16-bit. When the source is 16 bits, the the syntax is going to automatically take the concatenation of register DX with AX and divide that with the source 16, which you specified in here. Where the result goes, the result is going to be stored in AX register. How about the remainder? The remainder is going to be stored in DX register. Here's an example. We have CX register. CX is 16-bit. Therefore, you have your DX concatenated with AX is going to be divided by CX. And then the result, the quotient is going to store at AX register, and the remainder is going to be stored at DX register. Therefore, you have your DX, AX, the remainder with your source, which is in this case is our CX register. Here we have the same things for the memory location A. Since it is word, means that this is 16-bit. Therefore, when we want to divide when the compiler wants to do this operation, it automatically takes DX concatenated with EX register and divide it with bracket A. Same thing for this operation. AX and DX respectively store the value of the quotient and the remainder of the operation. For 32-bit, the same, just follow this. In this time, then your register EDX concatenated with EAX is going to be divided by source 32. And again, for the remainder, the result is going to be stored in EDX register and the quotient in EAX register. Just follow this example as the previous one, as the previous slide, and then we move to the next slide. In here, our source is 64-bit. In this case, we are going to consider the concatenation of RDX and RAX divided by source 64. Quotient goes to RAX, and the remainder goes to RDX. And here are the example for this operation. Here's the illustration of what we talk about. Same thing, but using graphical images. All right, if you want to know more about this mathematical and arithmetic operation, I recommend you to at least take a look at the first reference. It is a very good website, and the things, assembly code, are explained and expressed in a very simple way. Make sure to take a look at that. Okay, in division operation, error can happen. And then when we implement this kind of division operation, we have to make sure that we have to be aware of those errors and implement a mechanism. When this happens, you could prevent that or implement a strategy to produce the right result. Here's an example of what we have. We have EX register 0, EDX register as 1. You know that. And then we move ECX as 1, and then we call the division operation. So once we call the division operation, what's going to happen? Since this ECX is 32-bit, therefore, what is going to be divided by ECX is going to be the concatenation of EDX with EAX register. And this is going to be divided by ECX register, and the quotient is going to be stored in EX register, and the remainder is going to be stored in EDX register. So this is what we have in the previous slide. So let's see what happened in here. for this, we have EAX as 0 value, meaning that we have 0, 0. All these zeros are in hex. Therefore, since the register EAX is 32-bit and each of these number are 4-bit, therefore we're going to have 8 of these 0 hex. 1, 2, 3, 4, 5, 6, 7, and 8. And we said that register EDX has value of 1. Therefore, we're going to have 1, 0, 0, 0. This one also has to be 8. 0, 0. And this one is the hex number. It's not a binary number. It's a hex number. And then we're going to divide this by 1. So when you call divide, ECX is going to divide this value by 1. Therefore, whatever this value is going to remain because the quotient going to be equal to that. Therefore, when you, for example, divide 5 by 1, the result is 5. 10 by 1, the result is 10. In this case, when you divide this number with 1, your result is going to be this number again. But where the result goes into the quotient going to go to EAX register, right? But EAX register is 32 bits. And the result is in here 33 bits. Therefore, EAX register is going to have 0 value. And EDX register, the one that is in EDX register is going to be, EDX is going to store the remainder. Therefore, you are not going to take to get the value of 2 to the power 32. You are going to get the value of 0 because your EX register doesn't have enough bits to store this number. Therefore, the system is going to put an exception error. If you run this, then it's going to say that core dump, meaning that the destination doesn't have enough bit to store the resulting value of the division. But normally, when we use the division, the dividend and divisor are the same bit length. Therefore, this is going to happen rarely, but you have to make sure when you implement this, you also consider a corner case like that. So as you can see here, we say that it's going to be almost the same bit. We here initialize EDX with 0, then it's going to be concatenated of EDX and EAX. EAX is 32-bit, then this one is going to be divided by ESI, which is also 32-bit value. And then the result of this is going to be something about like 32-bit value. If ESI, the number that's stored in ESI, has about the same length almost. All right. So when you do the division operation and you store your number in EAX and you want to do division by ESI, you have to always make sure that if your number is not greater than 32-bit, you have to initialize the value of EDX with 0. Because if you don't do that, then you have your concatenation of EDX with EAX register, which is going to be divided by ESI for this example. And if you ignore the value of EDX, your result is going to be run. Therefore, when you do the multiplication and when you put your number in EAX, make sure that you initialize the value of EDX to 0. And for signed number, use CDQ. If you remember this bit extension from the previous lecture, CDQ used for signed bit extension. So these are for signed bit extension. Convert double word to quad word. When you do the CDQ, it automatically is going to convert EAX to the EX is 32-bit. When you do that, it's automatically going to extend the value of EAX to 64-bit, which is EDX, and concatenate it with EAX. So in here, the difference between this one and the previous one is that for the signed number, for unsigned number, is that if your EAX is a negative number, meaning that the most significant bit is 1, when you use CDQ, it's going to store value of 1 in each bit of EDX register, and then your EX register in here. So that's the difference. So for the unsigned number, you put 0, but for signed number, you can use this bit extension to take care of the signed bit for you. If the signed bit is 0, it's going to put 0 into your EDX register. But if the signed bit is 1, it's going to populate your EDX register with 1, 2. Keep the sign of your number. So we have a practice example in here for prime numbers. We want to write a program that reads an integer and prints if this number is a prime. We always assume that for this example that the input number is greater than 1. So let's see how we can implement this program. Okay, let's give you a very simple example first. Consider a number 7. When we want to see whether number 7 is prime or not, we start by dividing 7 to whatever number is less than 7. So we start dividing that number with 2, 3, 4, 5, 6, and that's it. So if you divide this number 7 with all the number smaller than itself except 1, and the remainder is not become 0, then the number is prime. If we divide this number to any of these number less than itself, and the remainder becomes 0, and the number is not prime. So if you take a look at this, we start by dividing 7 with number 2. 7 by 2 is going to be 3, and the remainder is 1. Since the remainder is 1, we move to the next number. We are going to try the next number and see if that next number, the remainder is going to be 0. So we divide that. So the remainder for this one is 1. Then we are going to divide 7 by 3. The remainder in case also is 1. And then we are going to divide 7 by 4. In this case, the remainder is going to be 3. Divide 7 by 5. The remainder is going to be 2. And then we divide 7 by 6. And the remainder is going to be 1. So in all these cases, the remainder is not 0. Therefore, our number is prime. If you take another example like 8, and we start dividing 8 by all numbers smaller than itself, so if you touch the 8, you want to check whether it is prime or not, you start dividing 8 with all numbers smaller than itself except 1 and see if the remainder is 0. If the remainder is 0, then the 8 is not going to be prime. So we are going to divide 8 first with 2. Therefore, it's going to be the quotient going to be 4 and the remainder going to be 0. Therefore, we immediately know that 8 is not a prime number. So this program is based on this algorithm. So let's see how we can implement that. Okay. So we first read the number from the screen. We read an integer from the screen. So assume that our integer this time is number like 4, and then we put that in EBX register, and we move value of 2 in ECX register. Why? Because we want to divide the input to all numbers except 1, and E6 this time is going to store all those smaller numbers than the input, so that we are going to divide that with E6 value starting with number 2, as we did in this example. All right, so we have E6 2, and then we are going to start a loop. We are going to compare if the value of E6 is equal to the greater than or equal to the number that we get from the input. So for example, if for this example we get number 4 and we start with E6, which is 2, we are going to compare 2 with 4. If 2 is greater or equal to 4, we are going to end the loop. But in this case, it's not. Therefore, we are moving to the algorithm. Okay, we move in here and then we move EBX into EAX register. Why? Because the division only works on the EAX and EDX register. We initialize the higher value of EDX with 0, and then we call the division operation. When we call the division operation, we basically divide 4 by 2, and then which the value is going to be 2. And this 2 is going to store in EX register, and the remainder going to be stored in EDX register. And in this time, the remainder is 0. The quotient is 2. So let's move on. So we move in here, we compare EDX with 0, and in our case, EDX, the value is 0. Therefore, we are going to jump to the label not prime label. So not prime label is in here. Then we put the not prime message into EX register and we print it out. What is not prime message? Not prime message is this one. So this one is going to be printed out on the screen saying that the number 4 is not prime. Okay, in case that the number is, for example, 5 going to be divided by 2, and then the remainder is going to be 1. Therefore, at this line, it's going to be compare EDX with 0, which is this time is 1 with 0. Therefore, it's not going to go to this label, it's going to go to the next line. Next line, we increase the value of ECX, which this time is going to be 3. And then we jump to the loop, a start loop, and this time E6 is 3. And then we compare E6 with value of 5 because we wanted to know if 5 is prime or not. Since E6 is still less than 5, we are going to move to the algorithm and not end the loop. This time, we put EBX into EAX register and we divide 5 by 3. 5 by 3, we divide, the quotient is going to be 1, the remainder is going to be 2. Therefore, when we compare EDX with 0, it's not 0. Therefore, it's not going to go to this level, it's going to be in here. In here, we increment the value of E6, and E6 this time become 4. And then we go to the loop again. This time, we compare 4 with 5. And since they are not equal, we are going to move to the algorithm again. And then this time we are going to divide 5 by 4. The quotient is going to be 1. EDX also is going to be 1. Therefore, we are not done. And this time again, we increment the value of E6 register. E6 this time is going to be 5. Therefore, we jump to the loop again, and this time we compare ECX with EBX. This time E6 is 5 and EBX is 5. Therefore, we jump to this end loop. Once we jump to this end loop, we are moving to this part of the program. And then in here, we print message. We take the print message, put that in the EAX register, and we print that out in the screen. And then we jump to the end L, which is the end of the program. So what's going to be printed out? The print message is going to be prime message. Prime message is going to print this out on the screen saying that, okay, number 5 is a prime number. Okay, So this is the algorithm that we have talked about, and this is another form of the algorithm for checking whether the number is prime or not. If you take a look at here, we compare ECX with EBX to check whether this is the program should go to the end of the end loop or not. But in here, if you take a look at that, we compare ECX with EAX, where EAX contain the quotient of the previous division. So this program, you can check this out by repeating the same example that I did in the previous one. And you will see that in terms of the complexity, this program is much more efficient than this one because the less number of iteration is required to identify whether a number is prime or not. This is the end of lecture 7. See you on the next video.